Hello, this is Vivek Singhal from CellStrat. I am a co-founder and data scientist at CellStrat. Okay, we'll just continue here momentarily. Just a sec. Yes. So as I said, I am Vivek from CellStrat. We are an AI startup based in Bengaluru, India. We do AI evangelism, AI solutioning, AI product development. Okay. Today we'll be talking about machine learning, the specific area within machine learning, unsupervised learning, which is primary algo we use here is clustering. Okay, so let's continue, keep going. Just a few logistics question. If you have any trouble in hearing or seeing the screen, just wave your hand through chat, and I'll see the chat, and I'll try to help you with the logistics issue. We are recording this webinar. Okay, this will be available on our YouTube channel by tomorrow morning sometime, in case some of your colleagues have missed it. Okay, and let's just continue the next slide. So just a plug on our startup CellStrat. We are a leading AI startup in India. We focus on emerging areas of artificial intelligence and deep learning. We are working on multiple solutions and innovations in this space, and we have a growing community of data scientists. All right. So just to set some context here about machine learning area in general, machine learning, as you know, relies on learning patterns based on sample data, whereas the traditional analytics was based on, a hard coding of rules by the developers in the program. Whereas in machine learning, we feed the currently available environmental data to the program, and it learns the rules based on that data. Okay. So that is sort of the major difference between traditional way of programming and the new machine learning, model training. Now, ML can learn from labeled data, supervised learning, or unlabeled data. Okay, so labeled data is where I have input X and output Y. For example, I want to predict house prices in Bangalore, so I would want the environmental factors, what are affecting the house prices, and then the corresponding house prices over last few years, and using that I can train a model to predict future house prices. And okay, so if you are having trouble in hearing this, then I request that you log out and log back in. Okay, and that should help you solve your hearing problem if you can't hear this session. If you still have a problem, just raise your hand and I'll try to address the logistics issue. Okay, and so as I was saying, supervised learning works on labeled data, and unsupervised learning where I have input X but no output Y from the past history. So I have to train some kind of model from that. I can't do all the things I can do with supervised learning, but I can still provide some value with unsupervised learning, which is actually the topic of the discussion today. Okay. And now unsupervised learning is a harder problem to solve because I don't have labeled training data available. Okay, as you can imagine. So we'll see how we do that today. Some other techniques in unsupervised learning. Okay, so now computers can obviously take subjective decisions. Well, for example, in a maternity hospital, when to recommend a normal delivery of a baby or a cesarean delivery. Another naive Bayes algorithm can separate valid emails from spam. So there are tons and tons of applications of AI and ML, and is getting hotter by the day. And the number of application areas is increasing every day almost. It's a very hot area, very interesting area to be in. Let's keep going here. Now, if you do have any questions, you can post them in the chat and we'll take them in the end just to save on time. We have massive content to cover in the short 1 hour today. So I'd like to keep moving at a fast pace. Okay. So let's discuss unsupervised learning today. If you have been on our past webinars, we have discussed some of the machine supervised learning techniques like regression, or classification. But today we'll be discussing unsupervised learning. And the primary algorithm, the most common one which comes under this is clustering. Okay, so we'll discuss clustering today. So just to understand overall category of machine learning and its uses, it's related to data science because a lot of the concepts of data science and data analytics we are using here. So that's why it's kind of symbiotically related to data science, the area of machine learning. And what are the broad classes of action which we could do? We could classify data, into let's say A, B, or C, a good email or bad email, and so on. Trend analysis like predicting house prices or how much it will rain tomorrow. Anomaly detection, like detecting credit card fraudulent transactions. and how data is organized, which is basically clustering or unsupervised learning, which we'll be discussing today, and decide on future action, which is deciding what should I do next. So this is called reinforcement learning, and we teach a model by giving it rewards and penalties and so on. Okay, so let's keep moving here. So coming to unsupervised learning, clustering specifically, here what we are trying to do is, for example, we are given a set of fruit images, and we are trying to classify them into citrus fruits or gourd kind of fruits, right? So this is one example of clustering, and we do not have prior labeled training data available. We are just given these images of these fruits and would like to classify them. Another example could be, identifying customer segments into urban, semi-urban, or rural populations. For example, for e-commerce, behavioral targeting, if you will, and so depending on the customer segment, you can show them custom offers on e-commerce portal. Okay, so this again organizing customer segments into clusters here. So just to understand, the difference between supervised and unsupervised learning once again, even though we have discussed it in the past. In supervised learning, we have these data samples, as you can see in the diagram below. We have input, x1 and output y1 for given that input x1, and so on for x2, y2, y3, y3. And then in supervised learning model training, I'm able to derive a relationship between x and y. So I learn or infer a function, something y equal to function of x, right? And then once I learn this function, I can put it in production, and then I can predict the future value y for any new input x once I have learned the function or the relationship between x and y. Okay, so that is called supervised learning, where I'm supervising the learning process by giving it labeled training data. The y is called the output ground truth label. Okay, let's look at unsupervised learning now. In unsupervised learning, I do not have labeled training data. The only thing I have is some set of input, some data samples, and I can't do a whole lot of things like regression classification with that data. But I could still do something called clustering, which we are discussing today. So we could use something called K-means cluster algorithm, where I can segment, a set of data into clusters or groups. For example, I want to segment news articles on the fly into different categories. So I want to assign sports related news articles to the sports section in the portal, and political news article to the political section, and so on. So I'm able to segment these news articles into different classes or portals or different sections of the portal, segregated by the topic. Okay, so this is just diagrammatically showing I'm given a set of data samples which has different features. Each data sample has two features, feature 1 and 2, and I'm able to find a clusters out of them. So I'm able to say, okay, this is belonging to the blue dots and this is belonging to the black dots. Okay. So one more type of unsupervised learning is visualization. So I'm given some set of data, and in this case, it's some kind of moving object, a mobile object, and I want to classify them into different kinds of vehicles or animals which can also move. So I want to basically, this is visualization. So I want to see those clusters, visually in a visually rich environment, and you can see that it is able to produce that kind of infographic image where the automobiles are in one kind, corner, trucks are in one corner, birds are in another corner, and animals are in another corner. So this is able to produce that kind of visualization and okay. Let me see if anybody has any questions. No, nothing yet. So far so good. Okay. So let's look at the third kind of unsupervised learning algorithm, anomaly detection. Okay. So those of you who cannot hear me, kindly log out and log back in. Some people are not able to hear me still. Okay. So if you're not able to hear me, my request to you is that kindly log out and log back in. Okay. So if you are still having a problem, just raise your hand in the chat, please. Okay. So let's look at anomaly detection. In this case, I'm trying to detect, for example, fraudulent credit card transactions. Okay. So I'm given any monthly credit card statement, and I want to find any credit card transactions which don't belong, and I would like to report on them. So this is anomaly detection, and we can also use it to detect, suspicious, elements in the society. For example, criminals. Okay. So I don't have past label data. On the fly, I want to try to detect certain segments of certain data samples. Okay. So just that was just a simple list of possible unsupervised learning algorithms, and here we see a general list of unsupervised learning algorithms, so which we could go through, but in today's 1 hour we'll just discuss clustering. There are quite a few. You can see autoencoders, dimensionality reduction, clustering, and association rules. So we'll be just looking at clustering for today, but this is a broader list of different kinds of unsupervised learning algorithms. Okay. So let's look at clustering now, which is our main topic today, which is one of the major types of unsupervised learning algorithm. In clustering, what is happening is I'm given these data samples you see in the diagram, and I'm trying to group them into clusters. Okay. So I'm trying to find natural groups. Okay. So, now there are three kinds of clustering algorithms. One is prototype based clustering, hierarchical clustering, and density based clustering. So we'll be looking at two of these in interest of time. We'll be looking at prototype-based clustering, which is basically K-means algorithm. Also hierarchical clustering. We will not be considering DB-scan today because of a small time period today. Okay. So let's look at prototype-based clustering. And here the primary mechanism is called K-means algorithm. And what happens in prototype clustering is that we say that each cluster is represented by its centroid or its average or medoid value. Most frequent medoid means most frequently occurring point. So basically, I'm trying to find the average of a group or the center point of a group. For example, let's say you have a classroom. Okay, so in a classroom, you could have a class monitor, sort of the center of a class, right? In a real student's class, and if anything which happens, sort of monitor would represent the class. Same way, in a cluster of data samples, we could have a centroid or an average or median point which represents the cluster or its primary characteristics. All right. So that exactly is what we mean by a representative point for a cluster, and we call it the prototype. So all the samples in that cluster are close to that prototype value, the center value, if you will. You know and each nation has its capital, so the capital is sort of the center point of a country, right? If you will, just giving a sort of a vague analogy there, but it seems to work. And now in K-means, what happens is we are trying to get training data, assign training data to matching cluster based on similarity. So in K-means, what we do, we try to find a cluster where data samples are most similar. For example, in a class of students, I may want to find bright kids from average kids from low performing kids. So I just spoke about three possible clusters in a classroom session. Bright kids, average kids, and then low performing kids. So I want to detect the three clusters so I can do their academic dealing appropriately, so that I can help the folks who are average or low performing and come them up, help them achieve a superior performance in academics. So this is called similarity matching, and it's an iterative process to get data points in the best clusters possible. So I keep trying these data samples in different clusters till I find the most closely matched clusters where each data sample within a cluster is very close to each other. Okay. So let's see some more details. So some examples here are given first. So examples would be grouping articles, movies, or music. For example, you find different genres of movies or music, and cluster them. Articles in a news portal we already discussed, and then finding customers who share similar interests. For example, when I'm selling e-commerce online, so I would like to find customers who prefer contemporary fashion versus those who prefer traditional clothing. So If I'm able to do clustering, I can show them the correct products on my e-commerce portal and personalize the experience, if you will. Also classifying high risk and low risk patient from a patient pool so that I can apply emergency procedures for my high risk patient pool in a hospital perhaps, or segregating criminals from a normal crowd in a security process. All right. So let's look at the mechanics of this entire algorithm. The K-means, as we are saying, is the most popular clustering mechanism, and this is hence it is the most popular unsupervised learning technique. Now, what is happening here is first what we do, we are given all these data samples which happen to belong to 3 different clusters. But initially we don't know that, right? We don't have clusters segregated when the data set is presented to us. So what we do, we just randomly pick, k number of centroids. K for knife is actually the number of centroids, let's say, and this is a subjective decision which a data scientist has to take. But we have a help how to figure out k a bit later in this presentation. But for now, let's assume we pick k to be equal to 3. Okay, so we are assuming there are 3 clusters here, and we pick, we arbitrarily pick 3, points in different areas, which we call them as centroids. So we are saying there are 3 possible clusters I'm trying to find, and I randomly pick 3 possible centroids. Okay, then I assign each of the other points to the nearest centroid, and such that the distance between the points and the centroid reduces to the maximum possible level. Okay, what I'm trying to do is try to assign points to a cluster in such a way that all the points are closely huddled around the centroid. Okay, I hope you understood that. So I'll basically keep trying these points in different clusters. I'll shuffle them around till I find the within cluster variation, within cluster distance is minimized, which means that the sum of distance of all the points in a cluster from its respective centroid should be minimized. I'll repeat that long sentence. So my objective is to minimize the sum of distances between all the points in a cluster from the respective centroid of that cluster. Okay. So for example, in this diagram, I find that all the green dots belong to that cluster there. They are closest to that centroid, shown by the star. All the blue triangles belong to that cluster, and all the yellow dots belong to that cluster, because the sum of distances from that centroid to each of those yellow dots is minimized by having this configuration. I mean, I would have randomly tried these points in different clusters. So what we are seeing in the diagram is the final configuration after having tried the points in different clusters and measuring distance of each data sample from the centroid point. Okay. So if you have any questions, just put it in the chat. We'll take it up in the end. For now, I need to keep moving. Essentially, I'll do this until I find that the distance is minimized, and or I could have a user-defined limit of how many iterations I do of this hit and trial. Because sometimes what can happen, the algorithm can go out of whack and just keep doing it, unable to find the minimum distance from centroid in each cluster. So you may have to forcibly stop it with a user-defined tolerance level. So I may say I'll give it 1,000 iterations, let's say, and no more. So whatever it finds, I'll just live with it. So now the problem with this algorithm is I have to know the value of k before a priori, if you will. So if let's say I chose k to be 2 here, so how will you segregate this data samples into 2 clusters? You can see all 3 are sort of separated. So if I had given k as 2 and only allowed 2 clusters, I would have poor clustering. If I had allowed k to be 4, again I would have poor clustering, because then where will you find the 4th cluster, right? So having the correct k is a limitation with k-means, and having to decide that in advance. But there is a technique called elbow method. We'll see in a subsequent slide where we can try to find an ideal value for the k, the number of clusters. Just to see the algorithmic logic behind k-means. So it is just mathematical representation. So if you look at these equations, they may look a bit intimidating, but really at the core they are very simple. If you see the first equation, I have 2 points x and y, and I am trying to just measure the difference or the distance between x and y, and x minus y squared. I just take a square, and my objective statement is to minimize this in the second equation. So SSE is sum of squared errors, okay, sum of squared errors, and then I'm applying appropriate weight as we do in supervised learning as well. And my objective is to minimize the sum of squared errors. So that's why there is a summation sign there. So first I sum it over data samples. Actually, I first apply a sum over all the possible K clusters, and the second summation is over all possible, data samples which are provided to me. So let's say there are 1,000 data samples, so n will be 1,000. If I'm doing 3 clusters, K will be 3. So I do that across the board for all data samples, okay, and I weight the distances appropriately, and then I take a sum of all of these across data samples, across clusters, and this SSC figure I want to minimize. When I minimize that, what would happen? All the samples would lie very close to their respective centroid. The centroid is represented by that value mu. So mu, that value mu which you see there is actually the sigmoid, the centroid value, and I'm trying to do it for every xi, and I'm trying to reduce the distance between data samples and the centroid value mu. Okay, so it's a very somewhat simplistic mathematical logic. If you understand it, it's not difficult. Okay, so we'll just keep going here. Now K-means, so in the code, if I were to do it in, let's say, if I was using Python scikit-learn, which is a popular machine learning, API, sklearn, and I can do import K-means, which is the library available to me, API available to me for machine learning. Okay, so K-means, what I'm doing here is I'm just calling K-means, and I'm doing a fit and predict. So in scikit-learn, with just 3 lines of code, I'm able to do clustering. So it's relatively simple. So the API in scikit-learn is able to abstract out, the complexity for me, right? And you can see I'm telling it K is equal to 3. So 3 clusters, please make 3 clusters for me. And, n init 10 means that, run the clustering logic 10 times with the random cluster centroids. And finally, the model with lowest sum of square errors will win. Okay. So I'm doing multiple, clustering algorithms, and I find whichever has lowest final. So I am creating 10 models really in memory. So whichever model has lowest SSE will win, and I'm allowing 300 iterations within each of the 10 runs of the process. Okay. So as I said, we are doing it multiple times to try to find minimum SSE, minimum sum of squared errors. Now, if I find that I've already reached minimum before 300 iteration, it will stop. Otherwise, it will basically stop at 300 iterations. Okay, and toll is another parameter which governs tolerance. So a large tolerance means it will declare convergence sooner. Okay, so basically this kind of code will abstract the complexity from me. I don't have to do low-level Python coding, to do K-means clustering. The API from scikit-learn will do the job for me. Okay, and then after fit and predict call, I will have clusters available for me. Let's keep going here. We'll be actually running this code at the end of this session, so you'll be able to see this in demonstration with proper plots being produced. Now, one of the challenge in clustering is that we have to preset the number of clusters, the value k. So that, and if we get it wrong, then we have bad quality of clustering, right? So, and we don't have ground truth level. So how do I find k? I find k by using some, this value called distortion. So distortion is within clusters sum of squared errors. Okay. So I'm saying I'll plot the number of clusters against distortion or the sum of squared errors, and then I'll see where I find a fit. Okay, so you can see the code there. It is just plotting at the end. It is just plotting the distortion graph. So let's go to next slide and actually see the distortion graph. So you can see the distortion graph. So in this graph, it pretty much explains to us what is going on. So it is trying this logic with different values of k. It tries it with 1, 2, 3, 4, 5, 6, and so on values of k, or number of clusters. K is number of clusters. Then it checks the distortion or the sum of squared error. So you can see when it goes from 1 cluster to 2 cluster to 3 cluster, the distortion falls rapidly. The sum of squared errors falls rapidly. But after 3 clusters, the relative advantage of distortion falling vanishes. So from 3 cluster onwards, there's not much advantage in clustering further. So I might as well stop at 3 clusters. See, we don't want too many clusters. We want to have minimum clusters, but still have clean segregation, if you will, right? If you have too many clusters, then it's too much micro segmented and it's not very practical. So we want less number of clusters. However, we also have a conflicting objective of minimizing distortion or sum of squared error. So we find a good point where k is equal to 3, where distortion is significantly minimized. Beyond that, I will not have much advantage in terms of distortion. So I can stop at k is equal to 3 clusters. I did not stop at k is equal to 2 clusters because distortion was still falling quite fast. Okay. So this is how this is called elbow method. The shape of this curve looks like an elbow. The elbow of a human hand. Hence, it's called an elbow method to find optimal number of clusters. Okay. Now let's go to second type of clustering mechanism, which is the hierarchical tree clustering. Okay. In hierarchical tree clustering, what happens that as opposed to prototype based clustering, we do not have to define number of clusters beforehand. Uh, you know we follow a hierarchy approach. So in agglomerative, there are two kinds of hierarchical clustering: agglomerative and divisive. In agglomerative, hierarchical clustering, we start with individual clusters and merge the closest clusters going up the tree, okay, until one cluster remains. In divisive clustering, we start with the top cluster, the one cluster, the root node, and we iteratively split the clusters until each cluster contains only one sample. So the only difference between agglomerative and divisive is we are going top down this tree or bottom up. In agglomerative, I am going, bottom up. In divisive, I am going top down. Okay, that's really the only difference between the two. But the more popular one seems to be agglomerative clustering. So that's the one we'll be looking at today. So agglomerative hierarchical tree clustering, there are two mechanisms. Okay. So what we do here, see, I told you what is agglomerative. I take individual data samples as their own cluster. So when I start this process, each data sample is its own cluster. It's not even merged with any other data samples in the world difference. So I assume each data sample is its own cluster. Then I find across and then I keep combining them. So I go up the tree. Now how I combine them? So there are two ways I could combine them. So let's say there are two clusters here. I could look at the nearest 2 points, the blue point and the brown point, the top line, and most similar members. We call it single linkage. So I find whichever are closest, I just merge these two clusters. I mean, you remember that tree, right? I have to go up and keep merging clusters, if you will. So to find which two clusters to merge, I merge the clusters which have most similar members. It's called single linkage mechanism. The other mechanism is I find the farthest points in the two clusters, the blue dot on this extreme and the brown dot on that extreme. Okay, and so whichever are the closest, this distance, whichever two clusters have this particular distance as closest, then I merge those two clusters. Okay, so I want to make sure the extreme points are under consideration now as opposed to the nearest points. Okay. But in both cases, by the way, both those dotted lines, I am trying to find the minimum distance. I'm trying to find clusters which have the minimum distance. You know, so that fact doesn't change between those two dotted lines. I'm trying to find the minimum distance points. Only thing is either I am comparing the nearest points or the farthest points in those two clusters. Okay. I hope this is clear. And this is called complete linkage. Okay. Uh, let's keep going here. So agglomerative hierarchical clustering, and we'll be looking at complete linkage particularly today. What it does, it computes a distance matrix of all samples. Okay, represent each data point as a singleton cluster. So initially, let's say I got 100 points, so each will be considered its own cluster. I merge the two closest clusters based on the distance of the most distant members. So if you remember from the diagram before, whichever 2 points are distant in two clusters, I find distances between them, and whichever has the minimum distance, I merge those two clusters first, and then I update the similarity matrix again, and again I go around finding the minimum distance between distant members of different clusters. Okay, so I iteratively do this process till the first cluster remains. Okay, So I'll just take a step back and go back so that we can understand this. So remember, in this tree, I am trying to go bottom up. So first, I'm trying to find samples in two clusters which are similar, close to each other, and merge them into one cluster and keep going up in that fashion. Okay. And in complete linkage, I am considering the points which are farthest across two clusters. Okay. So my area of interest in this particular algo so far is complete linkage, and I'm considering the farthest 2 points. So I find I create a table of these distances across different clusters between any two cluster combinations, and whichever have the minimum distance, I keep merging them. Okay. So this is the logic, and I do this iteratively till one cluster remains. All right. So let's see that more clearly with an example. So I'm given, these 5 data samples, ID 0 to ID 4 are 5 data samples. Each of them have 3 features, X, Y, and Z. Okay, 3 features for each data sample. So totally I have 5 data points. It just so happens that each data point has 3 possible features. For example, it could be age, height, weight, right? For a healthcare patient database, if you will. Okay, so that would be X, Y, Z. So I have 5 such patients available to me. Each of them have age, height, weight given to me. So what I do, I create a similarity matrix. You can see in their matrix there that I calculate the Euclidean distance or the distance between each pair of sample points. Okay, and and we use this kind of code to basically we can see this matrix being printed by this code, and I'm comparing the distance between different combinations of data samples. So between ID 0 to ID 1, ID 0 to ID 2, distance between ID 0 to ID 3, and so on. Now, if you notice, the diagonal is all 0. Why? Because it's the same point. So I distance between ID 0 data sample to ID data sample has to be 0, right? ID 1 to ID 1 has to be 0. So I am listing distances between every two combinations of data samples, and then what I simply have to do, as per agglomerative clustering algorithm, the whichever is the minimum distance, I'll merge them, right? So you can see here, the distance between ID 0 and ID 4, which is 3.835396, between ID 0 and ID 4. It is the minimum value. So I'm going to go ahead and merge them in as first, upward pass in the decision tree. Okay. Let's see that. So you can see that in this table here, I merged the ID 0 and ID 4. And then it so initially I started with 1 point each in ID 0 and 1 point in ID 4 cluster. I merged them. Now I have 2 items in that cluster. Okay, and distance was 3.83, if you remember. So I merged them. That was the minimum distance. And then correspondingly, I also found the distance between ID 1 and ID 2 is 4.34, which is the next highest distance. So I merged them as well. And then when I merge 0 and 4, I get a fifth cluster basically, and then I merge. I actually get a third cluster, and I merge it with the fifth ID5 data point. So let's see that through a different kind of diagram to make it clear. So this diagram will make it clear. So you can see ID 0 and ID 4 had the minimum distance, so I merged them first. And at the same time, I found ID 1 and ID 2, which had a distance of 4 point something, if you remember. I merged them as well. Okay. So the merger of ID 0 and ID 4, it takes me to something called ID 5 cluster. And then I merge ID 3 and ID 5. So the first blue merger there, the blue line merger, represents merger between ID 3 and ID 5 cluster. And ID 5 cluster was formed by merging ID 0 and ID 4. So if you look at this table, and then finally I merge, ID 6, which was formed by merger of ID 1 and ID 2, with ID 5, and have the final blue line at the top. So this diagram is pretty much explains what happened in the table you see here, right? So this table is not so clear, but when you see the diagram and relate to it, it is very clear what happened. I merged 0 and 4, I merged 1 and 2. So 0 and 4 led me to cluster 5, ID 5. I merged the remaining ID 3 with ID 5, and then finally I merged ID 1 and 2 led me to merge cluster of ID 6, and I 3 and 5 led me to merge cluster of ID 7. Then I merged the remaining two. So if you relate it to this diagram here, it pretty much clears the order of merger which is happening. So as you can see, as you remember in that tree, I am moving upwards. Progressively, I am merging the clusters, right? And finally, at the top, I have one blue cluster. That blue line represents that one final cluster. Okay. So we'll be seeing that in the code. Now the same logic can be represented by something called dendrogram, which is kind of a heat map. And that actually the diagram before was called a dendrogram, and I can relate it to a heat map. Okay, so you can see ID 0 and ID 4 are very close. That's why the orange and the red color is close. So it's like a colored heat map, if you will. And then ID 2 and ID 1 are close, so they are merged. And then finally I merge it with ID 3. The 0 and 4 creates ID 5, and I merge it with ID 3. So you can see the color, match. A color will be closer. If the color is closer, I happen to merge them. Okay. So it's a relative intensity of the heat, if you will. So this is a classic heat map, which is used in other kinds of heat map logic also. And the color of the cell represents how close they are. If the intensity of the heat is very close in those clusters, so I end up merging them. Okay, it's just a intuitive visualization of the whole thing. It's not like doing anything. I was just visualizing the merger process of agglomerative, clustering going up that tree kind of structure. Now, code-wise, again, it's very simple to code this. So while that logic it looks a bit daunting, but in scikit-learn, which is a Python machine learning API, I could just call agglomerative clustering API, and it will do the job for me. I don't have to, program the logic behind agglomerative clustering. The API will encapsulate that logic. I can call it, and I am telling it that I am, looking for n clusters. So n clusters 2 here means it will return 2 clusters only using the complete linkage approach. Okay. So n clusters allows me to prune the agglomerative clustered tree. And essentially what I did was that I used the API from scikit-learn. So it abstracted out the complexity of the algorithm from me. I did a fit and predict to do model training. And then I can see the clusters level. I can print them out. Okay. And since I allowed 2 clusters, so you can see there are out of 5 data points, there were 3 zeros. So the 3 zeros belong to one cluster, and the 2 ones belong to the second cluster. So I created 2 different clusters. So that's it for today. But let me show you the actual demonstration of the code, how this worked, and that will really help. Okay, and then we can go to questions. So I'll just quickly walk through this code. I hope you can see my screen here. I'm using a utility called PyCharm, which is a common IDE or development environment for Python code. And I have written so I'm producing, make blobs mean make, binary lobs. Basically, it's producing arbitrary data samples. I'm producing 150 data samples for demonstrating my problem here. And I just print them out. And then I run K-means algorithm using 3 clusters here. All right. And then I do a fit and predict, and then I just plot the clusters. This is plotting logic using matplotlib library of Python. And after that, I'm doing distortion check to find the appropriate number of clusters, right? We discussed the elbow method for finding appropriate number of clusters. So this is it will be plotting the elbow method, graph. If you remember that elbow kind of shape. And then I am also showing you an example where we can do low quality clustering. So if I were to do 2 clusters with that 150 data sets, we'll see what happens. So once we plot it, it will become clear to us. And finally, I'm going to do the agglomerative clustering on those 5 data samples, ID 0 to ID 4, if you remember. So we are going to do agglomerative clustering and see what happens, okay, using complete linkage mechanism, okay. And I'm not going to run through the whole code. Then I'll also draw dendrograms, as we saw that diagram is called dendrogram. And we'll also plot the heat map for that dendrogram. Okay, so that's it. So let me just run this and see what happens. Should be interesting. So you kind of ran through the program. Hopefully you understand it. So as you were seeing in the code, we are producing randomly 150 samples, and we produce them in such a manner that they sort of form 3 clusters. Okay, so this is a data set which we produced from the code on the fly. We are not using any existing data set. We are producing our own data set for testing and clustering code. And see, so I applied the K-means algorithm, and it is able to classify those points which I gave into 3 clusters using, and it found the appropriate centroid just by trying these points in different clusters and trying to minimize the distortion or the sum of squared errors. And what is sum of squared error? Is the square of the difference, the distance between a respective data sample and its centroid, and the sum of all of that per cluster. Okay, that is called sum of squared errors. So again, using ideal elbow method, I'm trying to find appropriate number of uh, I'm trying to find appropriate number of clusters. As you can see, it is saying that 3 clusters would is ideal value. After that, there is not much benefit to be gained in terms of reducing distortion. What is distortion? It is the sum of squared errors. So since going from 1 to 2 to 3 clusters, distortion continued to fall at a rapid pace. I kept trying, but after 3 clusters, I don't see any material advantage because it will make it, as I said, I don't want too many clusters. I want limited clusters, but 3 seems to be an ideal number here. After that, there's limited advantage only. So now this is an example when I enforce only 2 clusters. I manually set k is equal to 2. Just guess what happened. When I set k equal to 2, it tries to find 2 clusters. As you can see, it found 2 centroid, one here, one here. So the green one is good enough, right? But the problem is this one cluster. It is trying to find one centroid for these 2 sets of data, but it's not doing good clustering. This is called bad clustering. So because that means my value of k of equal to 2 is not good choice for this kind of data sample. So by elbow method, I saw I should have tried 3, but I forcibly set it to 2 to see a plot of a bad cluster example. So this is what we call a bad cluster. Now coming back to our agglomerative clustering, as you can see, it combines ID 0 and ID 4 first, as we saw on the PowerPoint slides. Then it combines it with ID 3, and on this side it has combined 1 and 2. And why it is combining these? Because it is measuring the distance between the most dissimilar members of different clusters, right? And then whichever minimum distance, it merges them. Okay, keeps merging them till I am left with one cluster at the very top. So this is called agglomerative clustering, and this is the heat map. Okay, so the left diagram is called dendrogram, right? Dendrogram, and then there's a corresponding heat map. It just shows in the heat map format which clusters were chosen to be merged. Okay, so that's it actually for today. Now we can take some questions if you have any. So kindly post any questions if you have in the in the chat window, and we can answer them. We still have 15 minutes left, so we can take questions if you have any. Any questions, please? Okay, I see a question here. So the question is, yes, so somebody saying, dear Mr. Vivek, I've got a question. Yeah, kindly go ahead and ask your question. So one question I see here is, can we do clustering on non-numerical data? Well, you can. So it's really, it's the distance metric. So as I said, it could be non-numerical data. In machine learning, if you remember, even categorical data we could convert into numerical data. For example, I have 3 categories, right? So let's say I have I have 3 categories: good, bad, ugly, right? Good, bad, ugly. So I could convert them into 0 0, 1, 2. So I could convert even categorical data into numerical values like good, bad, ugly will become 0, 1, 2. So I could find, I could still do clustering with that kind of categorical data. So yes. And do you use Python language code because it's more flexible than C++? Well, Python is the most popular machine learning programming language, but there are machine learning libraries in C++. You can try them, but Python has become sort of a de facto machine learning language, which is being used for machine learning and deep learning both. So I do recommend Python. I mean, I'm biased towards it. I work in it, but I've been a C++ developer in the past, and that will be fine as well. But C++ is a harder language to learn any which ways. So Python is recommended. I mean, R also sometimes people use, but Python is more popular for machine learning now. So, any other questions? I don't see any other questions so far. How to classify new data points based on K clusters? See, this I I I would have to retrain the model. Let's say I had 150 data points in that example I showed you. Now you send me another 50 data samples. So instead of 150, I have 200 data samples. So I have to run the clustering algorithm again to find new clusters, right? It's not like I have a pre-trained model. This is unsupervised learning. In supervised learning, I would have pre-trained model for classification, and I would just apply that for new data samples which are coming into the system. But here, there is no such concept. I don't have a pre-trained model. I trained it on 150 data samples to find clusters. Now I'll have to do retraining. If you send me, let's say, 50 more data samples, I'll have to find clusters among 200 data samples using the same exact logic. Okay, any other questions? All right, so I don't see any other questions. So thank you very much for attending. We'll be continuing our webinars, next week after the Republic Day of India. And thanks for attending, and hope to see you again next time. And this session is being recorded. It will be available, on our YouTube channel by tomorrow. A question just came in. Let me see what is this. How do we know which algo to use? See, this is experienced, data scientists. So, if I don't have labeled training data available and I'm asked to do classification or clusters analysis, so I would do this kind of K-means clustering, which we just demonstrated. But otherwise, overall, in the scheme of things, what data sample to use, it is based on, you know, uh, experience of the data scientists who have tried, who have taken different courses and who are certified or trained as data scientists. So we have number of training options within CellStrat. We work with other training partners and have our own training program. So if you have any questions on that, kindly contact us offline. We'll be happy to guide you towards right training programs. Okay, and that will help a lot in terms of becoming a data scientist. I don't see any other questions. So thank you for your time. Thanks all.